these bugs tend to hang on a little bit too, so please wash your hands frequently. If you've caught the bug, then make sure that you keep a low profile. If you have a fever, don't come to school. When you do get back, check out the DVDs and watch those, and then try to keep a low energy level, because what apparently happens is if you start zooming along like usual, it'll come back at you again. So I'm recovering as well. Okay, today what we want to do is we want to go back to some very basic material, but we want to kind of look at it in a new approach. Yes, okay. We want to look at linear functions, which you have quite a bit of familiarity with, but what we want to do is start taking some real information, data that behaves in a linear pattern, and see how to model that data with this linear function modeling processes. So what we're going to do for the data modeling is we're going to learn how to use our technology, and you can do this by hand too, except by using the calculator, you're going to find it much more efficient to use the data saving characteristics or capabilities of the calculator, and then be able to generate something called a scatter diagram. So what we're going to do is we're going to store data, and then we're going to generate a scatter diagram. And then we're going to let the calculator use some statistical features to create what's called a regression line, or the line of best fit. Line of best fit. And the modeling we're doing today, as I said earlier, is we're gonna take data that appears to be linear in its characteristics, and we're going to use our concept of slope and our slope-intercept type of an equation, which you're familiar with from beginning algebra, and then also this one, which is called what? What's the name of this? Point. There's a given point, isn't there? x1, y1, and a given slope, and so that's called the point-slope equation of the straight line. All right? So let's. This is in the beginning of chapter 3, so let's go ahead and grab something right out of chapter 3, and I think I'll throw it up here on the overhead and show us how to help you learn how to do that. First, look at this cluster of problems down here at the bottom of the page. This is taking you back to your beginning algebra background, these problems down here. Linear functions are given, and you'll notice it says determine the slope and y-intercept. Let's go ahead and kick up onto the overhead. There we go. And it says determine the slope and the y-intercept of the function, use the slope and intercept to graph the equation, determine the domain and range, and then determine the average rate of change, and is the linear function increasing, decreasing, or constant. So this takes you clear back to beginning algebra level with a little bit of college algebra vocabulary thrown in here. So let's grab one like number 18, has a little more something instead of a beginning level one, but maybe something like number 18 down here. Okay. So h of x is given to us as minus 2/3 x plus 4. It's very elementary, and you all should be comfortable with it. H of x is given as negative 2/3 x plus 4. Okay? Very clearly, the y-intercept is what? y-intercept is the point 0, 4, right? Easy. The slope is negative 2/3. So with that information in mind, we could draw a sketch of this. We have to have a point to draw a linear function to get started, and then from that point, we then essentially stair-step our way in the defined criteria for slope, change in y over change in x. So we know that we would drop 2 and run over positive 3, and continue to do that, drop 2 and over 3. And so we get a series of points other than the 0, 4 location. Now what we could do is we could go back to the original equation and just find some other point instead of playing the stair-step game with our slope. Instead of doing the stair-step thing like you would in beginning algebra, we could just simply come back and take some other location besides x equals 0. So we could go to some place like, say, I would select an x that is divisible by 3, like 3 or maybe 12. How about if I pick 12? Oh, I like that. Okay, we'll be out there to the right of ways. Let's go ahead and put a 12 in. h of 12 is minus 2/3 of 12 plus 4. And so all you have to do is find another spot, because we know the function here is linear. So we know it's going to behave like a straight line, so all we need is a second point. We've got this point already locked in, and all we need is some other point. So I'm going to go way far away from that, clear out at 12, and I drop it in there, and I get negative, that becomes a 4 times 2 is negative 8. Negative 8 and 4? Negative 4. So we have a point, another point then out at 12 and down at negative 4. So we can go out here. It's going to be out here a ways. 12, negative 4, right out there. And then we're going to draw our line. Okay. Now, to answer those fundamental questions that were asked in the book, it asked a variety of questions. It said, well, why don't you tell me what it says, since I don't have the book right here in front of me. First thing it asked was,
determine the slope and y-intercept.
Here's the slope.
Y-intercept.
Y-intercept, we did that.
Use the slope and y-intercept to graph the linear function.
Did it. Including, notice, labeling a couple of key points to help us.
Determine the domain and the range of each function.
The domain, clearly.
Negative infinity to...
Everybody feel good? Negative infinity to the left, infinity to the right. See, I'm just making sure we're all up to speed on this stuff before we start doing some data modeling. And then the range. Negative infinity, as low as it can go, keeps rising up off to the left in this case. Right? It asked that. And what else did it ask?
Determine the average rate of change for it.
Oh, average rate of change. Average rate of change. All that is, and I've mentioned this previously, is what? It's the slope. It's the slope. It's the change in y divided by the change in x. And in this particular problem, since the behavior is linear, the slope, the average rate of change is negative 2/3. So there's your average rate of change. Any other questions asked? Is that it?
Determine whether the linear function is increasing, decreasing, or constant.
Okay. Somebody else help me on this now. It's decreasing. Why is it decreasing?
Down to the right.
Because it falls to the right. falls to the right. So it's a decreasing function. Okay, so that covered all of the elements. All right? So let's now look at a set of data, or maybe we could find a problem, an application problem that, let's try to find something sort of real that's in the book, and then learn how to, let's come back right over here for just a second. Let's find something that's going to give us some data, learn how to store it in our calculator, or you could do it by hand by building a little table of the data, and then generate a scatter diagram either by hand or using your calculator, and then finally look at the data's graph and then generate a line of best fit. Once you have the line of best fit, you can then answer all of the kinds of questions that we're asking this basic question problem here. Okay, so back to the book. Let's take one like number 28. Like number 28. So what I'm going to do is, just in the interest of completeness, since I'm going to be using the calculator here in a few minutes, what I'd like to do is go ahead and write this information up on the board. So we have a collection of data. -10, -5, 0, 5, and 10 on the x, and the y data associated with those points is 0, 1, 4, 9, and 16. Okay, so here's data. Looking at this data, is it linear? Is this data linear? What would have to be the requirement for it to be linear? For any change in x, in this case, plus 15 is a change in x, right? Isn't that what's going on between, oh, hold it. From -10 to -5? What's the change there? Positive 5, isn't it? Okay. So for any change in x, and notice that it's uniform, isn't it? We have a uniform change in x from each data point, don't we? So our change in x is a +5. What's the associated change in y that you see over here? Change in y is +1 to here, +3, +5, +7. So is this data linear? Is there a constant change in, is this constant? Question? No, it's not, is it? It's not. What's the slope between these first two data points? I'm just adding more stuff to our table, notice. Between the first two data points, what's the slope? Help me. Speak up. Don't be shy. Change in y over change in x. Change in y is right here. Change in x. Help me. It's 1/5, isn't it? What's the change between the next two data points?
3/5.
Good. What's the change in the next? 5/5, which is? And between the last two data points? Okay.
So when they say it's staying constant, they're not talking about the range of y, like 1, 3, 5, 7, which it is a constant increase of 2. They're talking about it has to be the same as the x.
Well, this is the definition of slope, isn't it? Or average rate of change.
Right.
Average rate of change is defined as your slope that you're familiar with. Average rate of change. And what I'm pointing out to you from this set of data is that the average rate of change seems to not be constant. Okay, it's not constant. It's 1/5 between the first two data points, then it gets larger, 3/5 up to 1, and then 7/5, even greater than 1. Right? So is this data linear? No. So change in y over change in x constant? No. Okay, so the data is not linear. So what I'm doing is I'm showing you from a set of data how you can go back and discuss the issues related to slope or average rate of change just by looking at a data set. What are you more familiar with doing? Drawing a graph, aren't you? And looking at the graph. You're more familiar with looking at a graph of this stuff. So if I built a scatter diagram now by hand, a scatter diagram by hand, we can do that. And if I can do it here on a whiteboard with no grid, you can certainly do it on graph paper, okay? And so I can plot these data points. At -10, I'm at 0. At -5, I'm at 1. At 0, I'm at 4. At 5, notice I'm trying to, my scaling's a little screwy here. At 5, I'm up at 9. And finally, at 10, I'm at 16. Does that data look linear? Clearly, no, right? If somebody asked you, like if I asked you, how would you show me what these average rates of change are that we just discussed here on the graph, what would you draw? What would you draw on that picture? You would draw these slopes. Here's a slope. That slope happens to be what? Right there? 1/5. This slope, 3/5. The next one, slope of 1. Pretty good looking graph, huh? Okay. And then finally, a slope of 7/5 between those last two data points. Do you see how the average rate of change is increasing? Yeah. And so this function is growing, but it does not appear to be growing linearly, does it? Okay. Real world stuff does this. But you might take a trend like this and say, oh, I want the line of best fit, the straight line of best fit. So what we would do is we would look at this graph and we would probably, one way of doing it would be for us to take all of these values, and this would be kind of a pain, and average these together, average these slopes together. And what I'd be coming up with would be a slope, probably something like my hand here, right? If I averaged all these individual slopes. And then I would kind of look, where do I want to lay that line to get the line of best fit? Okay? So I just used my artistic talents to kind of eyeball where I would lay that line. Feeling good? Okay. So where would you suggest I lay it? Do you want me to just try it?
10, 16.
Actually hit that point?
Yeah.
I actually think if I've got these data values, maybe this is money. $16, $9, $4, $1, no dollars. Okay.
Okay, less.
So I'd probably come in a little lower than any one of those, or I'd be above some of the points and below some of the others, to make a long story short. So I'd probably just eyeball this with some line, maybe something like that. Okay? That'd be a rough guess. Now my sketch is not too bad, is it? I mean, considering I don't have any grid up here. So if I look at that thing, and I'm noticing that this point's here, down here at 4, that point's up at 9, it looks like my y-intercept might be somewhere, what, around 6 or so? 6? And what do you think that slope looks like, folks? Got a sense? 64 fifths? Oh, now that'd be huge.
About
wouldn't it?
one.
64 fifths would be big. So it'd probably be something less than 7 fifths. Reminds me of the 3 bears, right? Too cold, too hot, just right. Okay. So too small, too large, somewhere between these. How about 4 fifths? Doesn't look like, let's see, 1 fifth, 3 fifths, 5 fifths, 7 fifths. Why don't we guess 4 fifths? And it's just guessing based on the picture. Okay? 4 fifths. So if I guess a y-intercept, this is a guess, and I guess a slope here of this, then my model, my data model would be, this is my guess, this is my model guess, would be y equals what? 4 fifths x plus 6. Our model guess, just by rough sketching here, would be that for this data.
When you're doing a line of best fit, you always start at the bottom, but not necessarily at the point that crosses the x-axis.
Yeah, notice I'm not hitting this point. Matter of fact, I'm not hitting any of the points with my guess there, right? I'm too low here on my guess. I'm too high here and too high here and too high there and too low there. Got the idea? You can take a ruler. If you've got your scatter diagram, you can take a ruler and kind of wiggle it and kind of feel where you think it should fit. And then you can simply look at that sketch you drew with your ruler and go ahead and write down what you think is a guess. Okay? And so the slope in decimal form would be 4 fifths is 0.8, isn't it? 0.8. Y equals 0.8x plus 6 as our guess. Okay, so this is the way you do it by hand. Matter of fact, back in the days when I was in school, a long time ago, we didn't have these fancy calculators, and we would do it this way. We would do it this way. And we would be able to do things like when I went through engineering school pretty darn accurately. Accurate enough to be able to do things like get satellites up into orbit and stuff like that on a much more sophisticated level. But we were able to do a lot of that stuff without using calculators. We use slide rules. Okay.